Hello everyone, and welcome. Today I will present our CVPR 2026 paper, Real-Time Multimodal Fingertip Contact Detection via Depth and MotionFusion for Vision-Based Human-Computer Interaction. We enable precise virtual keyboard typing detection using only a single RGB webcam. No specialized depth hardware required. Hover and contact are separated by less than 3 millimeters. Yet state-of-the-art depth models produce errors of 12 to 25 millimeters, 4 to 8 times too large. Commercial motion capture systems achieve the required precision, but their hardware requirements limit accessibility. We demonstrate that a standard commodity RGB camera can close this gap. The root cause is a domain gap. Training benchmarks like NUUz depth v2 cover half a meter to 5 meters. Our VR keyboard zone is 20 to 40 centimeters. Nearly absent from all training data. Jensen-Shannon divergence of 0.576 confirms the domains are statistically near disjoint. Architectural improvements alone cannot fix a data problem. We built the first large-scale close-range dataset, 53,300 synchronized RGB depth pairs from 15 participants, 3 surface types, and 3 camera angles. Intel RealSense D405 provides ground truth at 0.3 millimeter precision. Split 8 to 1 to 1 by participant to prevent identity leakage. Our 3-stage pipeline runs at 30 frames per second with 98 milliseconds total latency. Stage 1. Media pipe extracts 5 fingertip coordinates per frame. Stage 2. Our fine-tuned depth model estimates metric depth per fingertip, back projected into 3-dimensional space and compared to the ransack-fitted table plane. Stage 3. A velocity-gated hysteresis state machine fuses depth with motion. Contact triggers at 4.5 millimeters with confirmed downward velocity and releases at 6.0 millimeters, preventing boundary oscillations. We fine-tuned 7 SOTA depth architectures on our dataset using scale-invariant logarithmic loss. Before fine-tuning, depth anything v2 produces 12.3 millimeters mean absolute error. After domain-specific fine-tuning, 3.8 millimeters, a 68% reduction, matching the performance of a dedicated Intel RealSense D415 hardware sensor. Critically, all 7 architectures improve consistently, confirming that targeted data, not model architecture, is the key bottleneck. Visually, the gap is stark. Pre-trained models produce blurry, featureless gradients. Individual fingers are indistinguishable, and errors reach hundreds of millimeters. Our fine-tuned model resolves each finger with sharp boundaries, enabling the millimeter-level discrimination that contact detection requires. This depth precision translates to contact detection performance. Our system achieves 94.4% F1 score with 94.8% precision and 94.1% recall. Per finger results follow a natural gradient. Index finger at 96.2% F1, pinky at 88.4%, mainly due to self-occlusion during natural typing. Comparing against commercial platforms from Table 4 of the paper, MetaQuest 3 achieves 35.2 words per minute with 8.4% error. Apple Vision Pro achieves 42.7 words per minute. Our system achieves 45.6 words per minute with 3.1% character error rate, the best on both metrics, using only a standard RGB camera without any additional depth sensing hardware. Here is our system running live. By manual typing at 45.6 words per minute. Contact events shown as green key glows at the exact moment of touch. Single RGB webcam, 30 frames per second, 98 millisecond latency. For key contributions. First, 53,300 RGB depth pairs, publicly released. The first close-range VR keyboard dataset. Second, 68% MAE reduction via domain-specific fine-tuning, enabling a standard RGB camera to match dedicated depth hardware performance. Third, 94.4% F1, 45.6 words per minute, 3.1% character error rate, outperforming all commercial VR platforms tested. Fourth, a general principle. For close-range HCI perception, targeted training data matters more than architectural innovation. All source code, dataset, and pre-trained checkpoints are publicly available on GitHub and Hugging Face at the links shown. Thank you. We welcome questions and collaboration.